Hello and welcome back. I believe we're in lecture number 4. We continue with complex variables. Today is our first contour integration, and we're going to look at a very simple integral of this particular type. When we're having limits 0 to 2 pi and the integrand some function of cos theta or sine theta. Of course, it could be one or the other or both. We can have sine squared, of course, that's part of the same type. And even if we have things like perhaps, I don't know, like a cos of 3 theta, that is still covers it because, of course, a cos of 3 theta can be expressed as cos of theta. So these conditions are satisfied quite clearly by this particular integral, which we're going to attempt in a minute. This type of integral, something that looks like that, of course, can be done usually with A-level further maths knowledge. We do it by the little t substitutions. I think the Weierstrass substitution is also called, by using the substitution t. I call them the little t substitutions. T is equal to the tan of theta over 2. They're not too bad. Sometimes the limits might cause problems. For example, here, if you look carefully, if we use this particular substitution, we're going to have 0 for the 0 and 2 pi is pi. So it's a little bit bizarre, 0 to 0. So I'm not quite sure. I have to really think about if I was to do it without complex numbers. Anyway, we're going to move into the complex plane in a minute. So how we do something like that? First of all, we're going to parameterize the integrand and the whole integration. So we're going to use a unit circle. For something which looks like that, 0 to 2 pi, telltale signs, we're going around a circle, okay? So we're going to use unit circle at the origin, traced in an anti-clockwise direction, using the most standard parameterization, that's real z and im z. And of course that is z is equal to 1, radius 1, e to the I theta, where theta runs from 0 to theta is equal to 2 pi. So we trace it in an anti-clockwise direction. We needed the z. The z is equal to I e to the I theta d theta. And then we observe actually the e to the I theta is z, so we might as well write it in terms of z there, as the z is I z d theta, and we're going to need to put the d theta in there. So let's make d theta the subject. D theta is dz over iz. We also need to change the cos of theta there to make it in terms of z. So the cos of theta, of course, we should know even from A level that this is a half e to the I theta plus e to the minus I theta. Basically what that says is the cos of theta is the same as the cos of I theta. So in terms of z, this particular thing would be the cos of theta is a half and e to the I theta is z, so it's going to be z plus 1 over z. So let's start putting our things in. Let me move this long cable. This mic has a hugely long cable. I'm going to trip on it one of these days. So, and let's see what happens. First of all, we're moving into the unit circle. Let's call this unit circle gamma. Okay, and what happens there? We're going to have 5 minus 4. The cos of theta is this bit here, so times a half z plus 1 over z, and my d theta is dz. Let's my 1 in there. My d theta is dz over iz. We're going to do a bit of a tidy for this particular one. So what can we tidy in there? So we're doing one step. Probably better to go safe. I'm very error prone, so I make a lot of silly mistakes. So 5 minus 2 lots at the front minus 2z minus 2 over z. And this iz, what I'm gonna do with this, first of all, let me put the z as that there, and the I, I'm gonna move it to the top as a minus I. So I multiply top and bottom by minus I, dz. Okay, last part of our simplification is to multiply it out. So we're going to get on the denominator 5z minus 2z squared minus 2, and we have of course the minus I dz, and conveniently, because this quadratic is a mess the way we got the negative on the z squared bit, so conveniently we got that minus on the numerator. So I'm gonna just move that in here. I'm gonna make some space so we can actually write a little bit neater. So we're gonna lose the minus, the I is still there, and this will become now 2z squared. We're gonna have a minus 5z, and it's gonna become a plus 2, and of course we're gonna have the dz. So what we've done so far is we managed to actually write this real integral, which is of course something, let's say there's our theta axis because it was in theta, f of theta or y, whatever you're going to call it. This is always positive, and some things that look like this, I don't know, 0 to 2 pi. Okay, and we managed to transfer it into a complex, into the complex plane around a unit circle. Okay, gamma in anti-clockwise direction. So this is what we've done so far. So far, no real complex numbers beyond A level really as such was used. So the next step is where the kind of undergrad maths comes in, and in particular we want to use the residue theorem. And for the residue theorem, we need to find residues of the poles of this function. This is my f of z. Okay, that's my f of z, which lies inside this unit circle. So I need to see where potentially I might be dividing by 0. So this is a quadratic, so it's very easy to, looks like it factorizes to, oops, I'm writing it again like an idiot. So let's factorize it, 2z, z, and it's a 2 on this side, 1 on this side, 4, 5, both minuses. Let's not forget the I. So it factorizes to this particular expression. So at the moment, clearly we have simple poles, and the simple poles are at z is equal to half, and this particular one is inside my curve somewhere there, while the other one is at z is equal to 2, so it's clearly outside the circle, and I couldn't care less about this particular one. So I just need to find the residue of the pole of f of z at a half. And we've done that on the lecture number 2 or number 3, I can't quite remember now. So let me just actually mark the pole here. So the pole in question is at z is equal to a half, and let me find the residue of this particular pole. To find the residue, we're going to use the simple formula that says the residue of f at some point, I'm going to actually write the point is a half, is the limit as my z goes to a half, z, oops, I was about to write x in there, apologies, z minus a half times my f of z. So this will be the formula for residues, which we revisited. We found, I think, about 7 or 8 residues another day in the previous time. Okay, so we need to start putting our things in. Limit as z tends to half, z minus a half, and now my f of z is going to be, I've got this I on the top, and I'm going to do 2 steps here rather than just writing it. I need to cancel, of course, that z minus a half should cancel with something denominator. Quite clearly is this term here, but at the moment I just need to pull out this 2. So I'm going to write a 2, so that's my 2z minus 1, 2z minus a half, so that's this bit here, times z minus 2, close bracket. And now this will cancel. as I'm expecting to cancel, and then I have a very simple limit which now it can be calculated. As I put z equal to a half, my I will stay on the top, and I'm going to get half take away 2 is minus 3 over 2. Minus 3 over 2 times 2 is minus 3. So I'll make this minus 1/3 I. Okay, so that's the residue. So I'm going to write, I'm going to rub off these workings, and I'm going to end this line as well. Don't think I need it. And I'm going to write up here somewhere that the residue of my f at the half is minus 1/3 I. And clear the board, and we're nearly done. We found the value for this integral practically for this in this particular case. Very simple, as I told you. Now, the residue theorem says when we're integrating around a closed curve, and the answer is always 2 pi I times the sum of the residues of f inside the curve in question, the closed path in question, inside gamma in this particular case. So what I'm trying to find, which is equal to that, is equal to 2 pi I times minus 1/3 of I, which of course is going to be a 2 pi over 3. The I times I is minus, times the minus is in fact plus. So the value of this complex integral is 2 pi over 3 when I'm integrating over the unit circle. But of course, this was parameterized to this particular, from this particular rather, real integral, and therefore the value of the integral we're trying to find, which is the integral from 0 to 2 pi 1 over 5 minus 4 cos theta d theta, is in fact just simply 2 pi over 3. And that is as simple as that for lecture number 1 on contour integration. If you want, I hope you enjoyed it. I hope you followed it. I'm talking a little bit fast. I'm trying to make the lecture a little bit shorter. Please leave in the comments below if you feel I'm going too fast or you need more explanations. And for the time being, who's laughing now? I hope you join me again for more stuff on this particular topic. Okay, bye for now.